Okay, well, good afternoon. So the first part of the talk today will be joint work with Nick Gravin and Balu Sivan, both postdocs at the Microsoft Research. Balu is in Redmond and Nick is in Boston. So maybe before starting with this formal part, let me emphasize, I'll be talking about the theory underlying this learning problem, but this type of learning occurs a lot in applications, including in Microsoft, and this is slides from my colleague Li Hong Li, who applies these kind of methods adapted to applied problems like that occur in a lot of applications inside Microsoft. And I just want to maybe highlight one application he does, which is to spell checking. So something as simple as spell checking, you may think, well, I just look up in I have a word, I just look up in some dictionary, there's a misspelled word, what's the closest word? But that's not really how it goes, because when someone misspells today, it's often because he's trying to type something which other people have been trying to type recently, because there are trends, and so it's really online learning that going on from what other people have been typing, and we want to each time we want to correct, and also to correct the spelling, see how the user responds to our correction. Does he like it? And then learn from it for the next spelling correction. So I won't focus now on this particular application, but kind of on the general theoretical problem of prediction or learning with expert advice. And really in this kind of problems there are two settings. Let me go back to the slideshow. There are two important settings. One is the full information feedback and partial feedback, which is called Bandit feedback, and I'll come back to distinguish between these later. I'll start with the simpler case of full feedback. So what is the setting? We have a sequential decision process, and we want to get here guarantees, so we're going to assume there's some adversarial setting. So we'll see what that means. So we have rounds, and in each round, the player, so that's us, the player will be the decision maker, okay, picks one of k experts to follow. So each of these experts makes a suggestion. Maybe this could be which road to take to work, or which route should we send our packets on the internet, or which stock should we invest in. So we have k experts, each one gives us a recommendation, and maybe some of them are very good, some of them don't know anything, but we initially can't differentiate, and over time we will know who is good based on their performance, but we don't want to pay too high tuition for this learning. So we don't want to use the advice of the faulty experts and only know at the end. So we have to balance this kind of learning with the rewards or losses we have along the way. So there are equivalent models here. We can think of gains or losses. If you just switch to, say, 1 minus the gains, you can think of those as losses. We'll start with just thinking of a gain. So so for each advice of the expert, say the expert told us, okay, which route to drive, there is a gain, which is how fast this route was. And once we chose which expert to follow, we have the gain corresponding to that expert. So we choose some index j, and then we get the gain j at time t. Okay. Now, again, in the full information case, we maybe know how all these different choices performed. But often, if it's roads, then maybe we only know how the road we chose performed. We don't know about the other options. So these are different models of feedback, and both of them occur in practice. again, we'll start with the full information setup where we get feedback for all the actions. Okay, so here are the, so this is the model at time t. We have the two experts. We know at time t all the gains. So these are the gains of expert 1 until time t minus 1. This is the same gains for expert 2. And now we have to decide at time t which of these to follow, and then we'll get the corresponding gain. Now if we have some policy, how do we evaluate that policy? So of course we could look at the total gains of that policy, but that's very dependent on the environment and what are the gains of the environment. So we want to really see how good the policy is doing. We need to compare it to a reasonable benchmark. So one benchmark you might think of is just the best optimal choices in hindsight, which are, maybe use expert 1 in the first round, expert 2 in the second round, 1 again in the third round, and so on. But this is an unrealistic benchmark. Choose selecting between the different experts at different times. So a more realistic benchmark is just to say, I want to compare my performance to that of the best expert. Okay, so, and I want to do at least as well as the best expert, or maybe since there could be many and it's reasonable to have some learning cost, then I want to do almost as well as the best expert. So that's the goal here. And now the other question is, when do we evaluate the policy? So the standard, most standard thing is to evaluate it at some fixed stopping time t. But there are other versions. One is that we don't know t and we have to evaluate along a variety of stopping times. And another is, which is actually very natural, is to say that we don't really know when the process will stop, but it might stop at any time, and maybe the probability of stopping is delta at every round, some small number. So an expectation will go 1 over delta rounds, but we can't say it will go exactly 1 over delta rounds. So this would be the case of a geometric distribution. So we'll mostly focus on this case, which has more nice stationarity properties, but also about the classical fixed horizon. Okay, so to determine the strategy, of course we'll use the vector of gains for all steps before time t, and especially important will be the cumulative gains of each expert. So gi of t is the gain of expert, the total gain of expert I by time t. So what we're going to think of this as a game between the player and an adversary who sets all these gains, trying to make life hard for the player. And so what the adversary sets at each time, we can think of him as setting the gains, or really, if he's using a randomized strategy, he's setting a distribution for the gains, which can depend on the past. Now, it will turn out, and I can explain this some more, that we can restrict attention to binary adversaries that just set gains to be either 0 or 1. Again, we assume that the gains are in the interval 0, 1, but in fact, it's enough to handle gains that are either exactly 0 or exactly 1. The point is that if there's a gain which was some number p between 0 and 1, it can be replaced by a coin toss, and you set 1 with probability p, and this will, and if the adversary actually did this switch, he would be better off. In other words, we, the decision maker, would have more difficulty dealing with this than with the original fixed p. So he might as well do this switch. Yes?
So adversary strategy doesn't look at players' moves for the...
So we can actually allow the adversary to look at players' moves, but right now I'm assuming the simple case that the adversary is worst case but oblivious to the player's move. So think of us, we're going in the stock market, but you and I, we're small players. Our purchases are not actually going to move the stock market. Okay, but some people, but then you have to consider that your own moves are having an effect. But now it's adversarial but oblivious. So the player strategy is a distribution AT for the choice J of which expert to follow time T, and again it can depend on the gains until time T minus in the previous rounds. And then his gain at time T is this GJT of T. Now the regret is what I mentioned before. It's the best. It's comparing our gain. So this is the gain of the player, this sum, and we want to compare that to the benchmark, which is the gain of the best expert. Okay. So this difference is the regret. Okay. And the goal will be to minimize the regret. So to choose an algorithm which, even against the worst adversary, will keep the regret as small as possible. When the regret is little o of t, we would say that we are learning. So on average, our regret per round is going to 0, but we want to make it even smaller than that. Regret, which is order t, is kind of a sign of failure. So our goal will be to control the minimax regret, because we get to choose the algorithm. So this is what, and our goal is to minimize, so we minimize over the algorithm. But then we're considering worst case, so maximum over the distribution of the adversary's choice of this regret I mentioned before. But a powerful method to analyze the regret is to use the Von-Neumann minimax theorem, which tells us that this quantity is the same as evaluated the other way, though intuitively these have different interpretations. So what's on the right-hand side, we maximize over the distribution of the loss of the gains. And then here there's the minimum on the inside. What that means is that we can think of an algorithm, a player algorithm, which responds to a known distribution of the that the adversary puts. So in this setting, we have to prepare the algorithm in advance, and it has to deal with all possible distributions of the gains. Here, we just have to have a good counter strategy for each individual randomized strategy of selecting the gains. But as long as we're dealing with randomized, then Von-Neumann tells us that these are the same. It's really a powerful fact.
So
yes.
So the player knows the distribution, or player just knows the sample?
So again, on the left, the player just knows the sample of what happened before. And so he has to, in advance, decide what is his strategy going to be, and then he's going to feed it to his computer. Now, the strategy, when implemented, each time it will see what happened before just the sample. So that's kind of what we think of as the real-life situation on the left. But our goal is to understand what this min-max regret is, and also to find good algorithms. Okay? So these are two goals. But if we use this equality, we're going to be less ambitious and say, suppose I just want to understand how this behaves without necessarily knowing what's the right algorithm to use. Then the minimax theorem allows me to do that. It allows me, kind of shortcut, to say I can find the behavior of the regret just by, for each choice of distribution, to find a good counter strategy. So on the right, I can assume that the player knows both the sample of what happened in the past. He doesn't know exactly what will happen in the future, but he knows the distribution and can compute computational distributions. Okay, but our goal will be, to use this, and then to maybe go back and find what is this great universal algorithm. But that's the goal. It's not always attained. Now, there is a very powerful algorithm in this area. I mean, there are several. Follow the perturbed leader is one, but multiplicative weights or edge algorithm is maybe the most famous. So what is this algorithm? It says, given the cumulative gains in the past, I'm going to choose one of the experts at random, but I'm going to prefer those with higher gains, but I won't choose only them. I have to maintain some diversity in the sample too. So I'm going to give a weight e to the eta times the gain of each player to that player, normalize these weights, and choose expert I with this probability. And then one can optimize eta, and for fixed horizon it turns out to be this is the optimal choice. And so this has a long history. Maybe I'll mention later some of these names, but actually the ideas underlying go back to Blackwell and Hanan in the 1950s. But anyway, this leads to regret of order root t. The dependence on the number of experts is, as you see here, is logarithmic, and even this is the sharp constant for t and k growing. And so this seems to be a complete answer, except this is a complete answer if t and k are both growing to infinity. Now, it's reasonable to think of the horizon going to infinity, but sometimes we just have two possible roads to go to work, or three stocks we're interested in, or three stock advisors that we have to choose between. And then this stops being optimal. It's only optimal asymptotically when both t and k go to infinity. And what we do in our work is focus on a fixed number of experts, k is small, and then try to understand what's the optimum there. Okay, so that's our goals here. Now, the optimal expert was, the optimal adversary was already found by Tom Cover in 1965, and this is it. Just that in every round, independently choose either, the first expert gets gain of 1 and the second 0, or the other way, and repeat. So think of it as very natural that this is what gives us the hardest time. And then, but I'll come back to explain why. Once we have this, it's clear what is the regret, because if this is really what the adversary is doing, then our choices don't matter at all, because what we're going to get is 1 or 0 equally likely, no matter which expert we choose. So we're going to get a random walk, but our benchmark will be the maximum of 2 random walks. And the maximum of 2 random walks beats 1 random walk by some constant root t. That's what's, and it's easy using the central limit term to find what is the constant, so it's root t over 2pi. And so this was already found by Cover in 65. Now we're going to focus on the case of geometric horizon, but because of the randomness of the horizon, you can't just replace this t by 1 over delta, which is the expected stopping time. You really have to average the root t, and that turns out to cancel the pi. And so what you end up getting is that the optimal regret, as delta goes to 0, it scales like 1/2 times root of 1 over 2 delta. And this is the exact formula. So it's actually, one difference is it's easier to calculate exact formulas for the model of geometric stopping time. You can do asymptotics in both. And actually going from this asymptotic to this one is standard Tauberian theorems. But to find exact answers, it's easier in the case of the geometric stopping time. So he described the optimal adversary. He didn't have a description for what is the optimal algorithm for the players. We're able to do that. So this, I'll tell you later where this comes from, but now let me just tell you what is the optimal thing to do here with 2 experts. And geometric horizon. So we set a number c, which is, this is the exact formula, but it's asymptotic to 1 minus root 2 delta, if delta goes to 0. Let me tell you what this c means. It's related to a random walk with geometric killing. Start such a random walk at 1, and the random walk is killed with probability delta in every step. And yes, what's the probability that such a random walk started at 1 will reach 0 before it's killed? This probability is exactly this number of c. Okay. and we'll see more serious connections to random walks later. Now, okay, so this is C. Now, what is the algorithm? For each T, compare the gains of the two players, so G1 and G2, and let D be the difference between them. Okay, if this difference is 0, so both players are doing the same, obviously we should give equal weight to the players. There's no reason to prefer one to the other. But if there is a difference, then we are going to penalize the lagging player by this C to the power D compared to the half. Okay, and then the remaining probability goes to the leading player. So what, see, it looks a lot like the multiplicative weights, except we're not multiplying everyone by weights and normalizing. Instead, we're just taking the lagging expert, multiplying him by his weight by C to the lag, and assigning the remaining probability to 1, and this turns out to be optimal. So it's not approximately for 2, because it is exactly optimal for all times. And you see the dependence on delta is just in this value sum. So I told you what psi is. Now the speed 2 of D, I gave you this form for it, but it also has a meaning for a random walk. So if we think of the total gains of each expert as some horse race, right, a random horse race, and you can ask, so the lagging expert could still finish first at the end. There's still some chance. The end could be a long time away because it's geometric stopping. So C to the half C to the D is exactly the probability that he will finish first when the game stops. So actually using this rule is a version of what's known as probability matching or Thompson sampling, which is a powerful method to balance exploration and exploitation. This method appears in many places. It's actually the first real paper on this type of problem is Thompson 1933, which didn't have any mathematics, it just had a proposal, but very powerful one. And this is an instance of that proposal. Usually Thompson sampling is not optimal. It's sometimes a good approximation. In this setup, it turns out to be exactly optimal.
Question?
Yes.
So is it optimal for every delta or only as delta goes to 0?
This is optimal for every delta. No, this is not as important for every delta. In fact, if you use this formula, you'll get something which is even optimal for fixed horizon T. But the probabilities then become harder to calculate. So, you have a random walk, you ask what is the chance that it reaches, it actually leaves a strip before some fixed time. This is something that has a formula, but it's a much more complicated formula. But this still works in that case. Okay, so this is a description in the words of the same algorithm. And it also, as I said, works for fixed horizon, but then the probability that the laggard finishes as leader depends both on the difference and on the remaining time. So what happens for 3 experts? Again, I'm just stating the results now, and I'll give some explanation of where they come from. So even the optimal adversary was not known until this work. And it goes as follows: with probability half, you assign the gains to player gain 1 to the first and the third expert, and with probability half just to the second. This is an optimal adversary. In this case, it's no longer unique. There are other choices, but this works. And one important thing is the numbering convention. So in this picture, it looks like I fixed the identities of 1, 2, and 3, but really I'm not fixing them. So when following this rule, you have to at every time reorder the experts according to their performance. So when I say with probability half, you assign gain 1 to experts 1 and 3. This is the leader and the laggard. Yes.
So it doesn't matter by how much they're leading relative to the middle one or lagging.
Right. So again, that's correct. But again, I emphasize, this is not the player's algorithm. This is the adversary who is setting the gains. So he is trying to make life as difficult as possible for the player, and yes, it doesn't matter by how much. Okay, and funny thing is, we think that one reason that people didn't find even this very simple thing is they didn't use this numbering convention. They thought, the experts have names and they use the names, and that is the wrong approach. You have to ignore the names and just look at the performance. Okay, and we can say what is the optimal regret. It's, so instead of half 1 over root 2 delta, this half is replaced by 2/3. And this is the optimal algorithm. So it again has the form of, so the C is the same one as before. And it again is a version of Thompson sampling, but let me explain it. So focus just on P3, on the one who is lagging the most. What weight are we going to give him? Well, if all the experts have the same performance, it should be 1/3. But if we have a laggard, we should penalize him by how much? So just by C to the sum of his lags over compared to the other two players. And this probability has to come from somewhere. So, so if you look at these formulas here, these were exactly, if we have only experts 1 and 2 in the game, then this is the formula we had for experts 1 and 2 before. So they are assigned the same probability as before, but minus half of the probability we just assigned to player 3. I'm sorry, to expert 3. Okay, so this is the formula, and again, this formula is, again, P3 of D is exactly the probability that the lagging expert finishes with leading expert. In this 3-horse race, but again with the rule that each time either 1/3 is advancing with probability half, or 2 is advancing with probability half. So we conjecture that something similar happens for larger K, but we can't prove it. For 4 we have a partial result, and 5 and higher we really don't know, but there is a conjecture. I'll tell you something more about that. So how do we arrive at these optimal adversaries? So they are simpler than the optimal algorithm for the player, and they are the basis of the next thing. So the key observation is that the optimal adversary is balanced. So what does that mean? So this exactly returns to your question. The distribution dt, so this is the distribution of the gains times t, advances all experts that is give them gains equally in expectation, irrespective of the history. So this I can actually explain. So why is that? So suppose an optimal adversary is not balanced at t. So in that case, the player who is responding to this distribution will follow the expert with the largest expected gain. Since this is a full information setup, there's no point in going. You don't have to explore the other experts. You always have to just go for the expert with the largest expected gain, because the next round it doesn't change the information you have for the next round. So that's true. Now, so therefore, at time t, suppose the adversary increases the expected gains of all other experts to match the largest expected gain. This will not change the choice of the best response algorithm by the player. It will not change his instantaneous gain, but it will increase the benchmark. So the benchmark is the max experts gain, and that is increased by this change. So if we are in an unbalanced situation, the adversary can change his strategy, improve it in such a way that increases the benchmark and doesn't increase the performance of the player, so it increases the regret. Since the adversary here is trying to maximize the regret, he will always use a balanced strategy. So as I said, the balanced adversary will advance all experts equally in expectation, irrespective of the history. So if we're playing against a balanced adversary, then the regret is independent of what we do. The regret is independent of the player algorithm, because the game in every step, the expected gain of the player doesn't depend on which expert he chooses. So as a simple-minded computational device, just suppose that the algorithm follows every expert with equal probability. So again, this is not a recommended method to ignore history, but it is just a computational device saying once we fix the adversary to be balanced, then it doesn't matter. So to compute the regret, we could use any algorithm, and we use the simple-minded algorithm, and then the regret is has this form. Again, when the gains are advancing according to a balanced adversary. Okay. So it's the max of the gain process minus the average. So the reason we would not the player would not want to use this strategy is because if he did, then he would be punished by an unbalanced adversary. But if we're just assuming a balanced adversary, we can use this as a computational device. So the regret is the max minus the average. Now let's go back to the case of 2. So if we take the max of 2 numbers minus the average, that's just the expectation of G1 minus G2. So in other words, if I denote by xt the difference in gains of 2 players, so this is minus 1, 0, or 1, I just have a random walk. But because we assume a balanced adversary, this is the mean 0 walk. And so the only choice we have to make in order to determine the adversary is what weight to put on 0. Because we have a distribution on minus 1, 0, 1. It has, so the weights on minus 1 and 1 are the same. But our goal is, so we basically have like a lazy random walk and want to maximize the expected distance from the origin, then it's obvious that you want to make it not lazy. You want to put the weight on 0 to vanish. And so this should just take values minus 1, 1, which corresponds to having the gain vector either 1, 0 or 0, 1. So this explains, covers theorem. It's not the same as his explanation. So we have a conjecture